All right, guys, welcome to Math Analysis. Today we're going to continue working on this worksheet right here, Avogadro's number and the mole. So, where we left off, we were talking about what to do if you are given a number of molecules you have, and you need to figure out how many moles of the substance there is. If you're working on some of these problems that we talked about on Friday, though, you'll notice that number 5 and 6, and the rest of the page really, change that up just a little bit. Here's what those say. Number 5 specifically says, how many atoms does 2.0 moles of helium represent? So here's what I want us to think about. Previously, we were talking about, there are 6.022 times 10 to the 23rd atoms in a mole. So what we were doing is we were taking the number of atoms we have and dividing it by how many atoms are in a mole to figure out the total number of moles. What we have divided by what there is in a mole, right? However, this is a little different. This problem doesn't tell us how many moles we have. It doesn't tell us how many atoms we have or molecules we have. It tells us how many moles we have. So you got to think about it a little differently. It's kind of the opposite thing. So here's what we want to think. If there's 6.022 times 10 to the 23rd atoms in a mole, and we have 2 moles, then all we have to do is multiply this number by 2, since we have 2 moles. Now, the kind of confusing thing here is how does multiplying just a single-digit number times Avogadro's constant, or any number in scientific notation, work? Well, kind of like the other day when we were dividing them, and we said that you divide the whole numbers separately, and you divide the 10 to the whatever power separately. We're going to do that here too. We're multiplying it by a 2. That 2 doesn't have any 10s attached to it or anything like that. So all that's going to happen is this 2 is going to multiply the 6.022. So 2 times 6.022 is going to be 12.044 times 10 to the 23rd. The scientific notation part of this does not change at all when we are multiplying these two numbers. This stays the same. It can change after we have done that multiplication and we have a new number in front of it. Here's how it changes. Scientific notation traditionally is used with numbers that are a single digit, such as 6, or, 3.5 times 10 to the whatever power. That kind of thing, right? But you'll notice now we have 2 digits in front of the scientific notation, or a 2-digit number, 12. I would accept this as a correct answer, but if scientifically, what we would usually want to do is take this decimal and move it over 1. Make it 1.2044 times 10 to the what? What's that going to be? Moving that decimal to the left is going to do what to that number? That's right. It's going to make it go up. It would make it 10 to the 24th, right? If the decimal were moving the other way, the number would go down to the 22nd. So we scientifically, the number we would probably use in a collegiate setting or something like that is going to be 1.2044 times 10 to the 24th. However, I am perfectly okay accepting 12.044 times 10 to the 23rd. The real thing I want you to get from this is that whenever you multiply something by however many moles you have, in this case 2, you're just multiplying that times the whole number, or the number portion of the scientific notation, not the 10 to the whatever power. There is another one of these problems, number 6. It says how many sodium ions are in 3 moles of NaCl. I want you to think about that. That's going to be a little different, right? Come back tomorrow. We'll talk about that one.